Everyone, my name is Santosh and I am a student of BSc Chemistry Honors second year. It's an audio video lecture of chemical bonding and molecular structure part 2, bond order. In the left description of covalent bond, the bond order is given by the number of bonds between the two atoms in a molecule. The bond order, for example, in H2, in O2, and in N2 is 1, 2, and 3 respectively. Similarly, in CO, the bond order is 3. For N2, bond order is 3 and its enthalpy is 946 kJ per mole, being one of the highest for a diatomic molecule. Isoelectronic molecules and ions have identical bond orders. For example, F2 and O2 2 negative have bond order 1, N2, CO and NO positive have bond order 3. A general correlation useful for understanding the stabilities of molecules is that with increase in the bond order, bond enthalpy increases and bond length decreases. Resonance structures. It is often observed that a single layer structure is inadequate for the representation of a molecule in conformity with its experimentally determined parameters. For example, the ozone O3 molecule can be equally represented by the structures 1 and 2 shown. In both structures, we have a oxygen-oxygen single bond and a oxygen-oxygen double bond. The normal oxygen-oxygen single and oxygen-oxygen double bond lengths are 148 picometer and 121 picometer respectively. Experimentally determined oxygen-oxygen bond lengths in the O3 molecule are same, that is 128 picometer. Thus, the oxygen-oxygen bonds in the O3 molecules are intermediate between a double and a single bond. Obviously, this cannot be represented by either of the two Lewis structures shown above. The concept of resonance was introduced to deal with the type of difficulty experienced in the depiction of accurate structures of molecules like O3. According to the concept of resonance, whenever a single Lewis structure cannot describe a molecule accurately, a number of structures with similar energy positions of nuclei, bonding and non-bonding pairs of electrons are taken as the canonical structures of the hybrid which describes the molecules accurately. Thus, for O3, the two structures shown above constitute the canonical structures or resonance structures, and their hybrid, that is the structure 3, represent the structure of O3 more accurately. This is also called the resonance hybrid. Resonance is represented by a double-headed arrow. Some of the other examples of resonance structures are provided by the carbonate ion and the carbon dioxide molecule. In general, it may be stated that resonance stabilizes the molecule as the energy of the resonance hybrid is less than the energy of any single canonical structure, and resonance averages the bond characteristics as a whole. Thus, the energy of the O3 resonance hybrid is lower than either of the two canonical forms 1 and 2. Polarity of bonds. The existence of a 100% ionic or covalent bond represents an ideal situation. In reality, no bond or a compound is either completely covalent or ionic. Even in case of covalent bond between two hydrogen atoms, there is some ionic character. When covalent bond is formed between two similar atoms, for example in H2, O2, Cl2, N2 or F2, the shared pair of electrons is equally attracted by the two atoms. As a result, electron pair is situated exactly between the two identical nuclei. The bond so formed is called non-polar covalent bond. Contrary to this, in case of a heteronuclear molecule like HF, the shared pair electron between two atoms gets displaced more towards the fluorine, since the electronegativity of fluorine is far greater than that of the hydrogen. The resultant covalent bond is a polar covalent bond. As a result of polarization, the molecule possesses the dipole moment, which can be defined as the product of the magnitude of the charge and the distance between the centers of positive and negative charges. It is usually designated by a Greek letter mu. Mathematically, it is represented as dipole moment mu is equals to charge q into distance of separation, that is r. Dipole moment is usually expressed in debye units, capital D. The conversion factor is 1 dBA is equals to 3.33564 into 10 raised to power minus 30 cm, where C is coulomb and M is meter. Further, dipole moment is a vector quantity, and by convention it is depicted by a small arrow and tail on the negative center and head pointing towards the positive center. But in chemistry, presence of dipole moment is represented by the Crossed arrow put on light structure of the molecule. The cross is on positive end and arrowhead is on the negative end. For example, the dipole moment of HF is represented as HF. The arrow is towards F. This arrow symbolizes the direction of the shift of electron density in the molecule. Note that the direction of crossed arrow is opposite to the conventional direction of dipole moment vector. In case of polyatomic molecules, the dipole moment not only depend upon the individual dipole moments of bonds known as bond dipoles, but also on the spatial arrangements of various bonds in the molecule. In such case, the dipole moment of a molecule is the vector sum of the dipole moments of various bonds. For example, in H2O molecule, which has a band structure, the two OH bonds are oriented at the angle of 104.5 degree. Net dipole moment of 6.17 into 10 is to power minus 30 km is the resultant of the dipole moments of two OH bonds. Net dipole moment mu is equals to 1.85 dB. The dipole moment in case of BeF2 is 0. This is because the two equal bond dipoles point in opposite direction and cancel the effect of each other. In tetraatomic molecule, for example, in BF3, dipole moment is 0, although the BF bonds are oriented at an angle of 120 degree to one another. The three bond moments give a net sum of 0 as a resultant of any two is equals to and opposite to the third. Let us study an interesting case of NS3 and NF3 molecules. Both the molecules have pyramidal shape with a lone pair of electrons on nitrogen atom. Although fluorine is more electronegative than nitrogen, the resultant dipole moment of NS3 is greater than that of the NF3. This is because in case of NS3, the orbital dipole due to lone pair is in the same direction as the resultant dipole moment of NH bond, whereas in NF3, the orbital dipole is in the direction opposite to the resultant dipole moment of the three NF bonds. The orbital dipole because of lone pair decreases the effect of resultant NF bond moments, which results in the low dipole moment of NF3 as represented here. Just as all the covalent bonds have some partial ionic character, the ionic bond also have partial covalent character. The partial covalent character of ionic bonds was discussed by Fazans in terms of the following rules. The smaller the size of the cation and the larger the size of anion, the greater the covalent character of an ionic bond. The greater the charge on the cation, the greater the covalent character of the ionic bond. For cations of the same size and charge, the one with electronic configuration n-1 dn and s0, typical of transition metals, is more polarizing than the one with the noble gas configuration ns2 np6, typical of alkali and alkaline earth metal cations. The cation polarizes the anion, pulling the electronic charge toward itself and thereby increasing the electronic charge between the two. This is precisely what happens in a covalent bond, that is, buildup of electron charge density between the nuclei. The polarizing power of the cation, the polarizability of the anion, and the extent of distortion of anion are the factors which determine the percent covalent character of an ionic bond. The valence shell electron pair repulsion theory, the VSEPR theory. As already explained, Leib's concept is unable to explain the shapes of molecules. This theory provides a simple procedure to predict the shapes of the covalent molecules. Sedgwick and Powell in 1940 proposed a simple theory based on the repulsive interactions of the electron pairs in the valence shell of the atoms. It was further developed and redefined by Nyholm and Gillies in 1957. The main postulates of VSEPR theory are: the shape of a molecule depends upon the number of valence shell electron pairs around the central atom. Pairs of electrons in the valence shell repel one another since their electron clouds are negatively charged. These pairs of electrons tend to occupy such positions in space that minimize repulsion and thus maximize distance between them. The valence shell is taken as a sphere with the electron pairs localizing on the spherical surface at maximum distance from one another. A multiple bond is treated as if it is a single electron pair, and the two or three electron pairs of a multiple bond are treated as a single super pair. Where two or more resonance structures can represent a molecule, the Vesper model is applicable to any such structure. The repulsive interaction of electron pair decreases in the following order: lone pair, then lone pair, bond pair, then bond pair, bond pair. Nyholm and Gillespie in 1957 refined the Vesper model by explaining the important difference between the lone pairs and bonding pairs of electrons. While the lone pairs are localized on the central atom, each bonded pair is shared between two atoms. As a result, the lone pair electrons in a molecule occupy more space as compared to the bonding pairs of electrons. This results in greater repulsion between lone pairs of the electrons as compared to the lone pair bond pair and bond pair repulsions. These repulsions effects result in deviations from idealized shapes and alteration in the bond angles in molecules. For the prediction of geometric shapes of molecules with the help of Vesper theory, it is convenient to divide molecules into two categories. First, the molecules in which the central atom has no lone pair, and the second, molecules in which the central atom has one or more lone pairs. A table shows the arrangement of electron pairs about the central atom A without any lone pair, and geometries of some molecule ions of the type AB, where the other table shows shapes of some simple molecules and ions in which the central atom has one or more lone pair, and the other table explains the reasons for the distortions and the geometry of the molecule. As depicted in another table, in the compounds of AB2, AB3, AB4, AB5 and AB6, the arrangement of electron pairs and the B atoms around the central atom A are the linear, trigonal, planar, tetrahedral, trigonal, bipyramidal and octahedral respectively. Such arrangement can be seen in the molecules like BF3, that is AB3, CH4 as AB4 and PCl5 as AB5, as depicted below by their ball and stick models. The Vesper theory is able to predict geometry of a large number of molecules, especially the compounds of p block elements, accurately. It is also quite successful in determining the geometry quite accurately, even when the energy difference between possible structures is very small. The theoretical basis of the Vesper theory regarding the effects of electron pair repulsion on molecular shapes is not clear and continues to be a subject of doubt and discussion. In this table, we will learn the number of electron pair, the arrangement of the electron pair, their molecular geometry and the examples. Number of electron pairs 2, arrangement is linear, molecular geometry is linear and examples are BeCl2, HgCl2. Number of electron pairs are 3, arrangement is trigonal planar, molecular geometry is trigonal planar and example is BF3. 4, tetrahedral are the arrangement, geometry is tetrahedral, CH4, NH4 positive are the example. 5, trigonal bipyramidal is the arrangement, trigonal bipyramidal is the molecular geometry, example is PCl5. 6, molecular arrangement octahedral, molecular geometry octahedral and example is SF6. Valence bond theory. As we know that Lewis' approach helps in writing the structure of molecules, but it fails to explain the formation of chemical bond. It also does not give any reason for the difference in bond dissociation enthalpies and bond lengths in a molecule like H2 and F2. Although in both the cases a single covalent bond is formed by the sharing of an electron pair between the respective atoms, it also gives no idea about the shapes of polyatomic molecules. Similarly, the Vesper theory gives the geometry of simple molecules, but theoretically it does not explain them, and also it has limited applications. To overcome these limitations, the two important theories based on quantum mechanical principles are introduced. These are the valence bond theory and the molecular orbital theory. Valence bond theory was introduced by Hitler and London in 1927 and developed further by Pauling and others. A discussion of the valence bond theory is based on the knowledge of atomic orbitals, electron configuration of elements, The overlap criteria of atomic orbitals, the hybridization of atomic orbitals, and the principles of variation and superposition. A rigorous treatment of the valence bond theory in terms of these aspects is beyond the scope of this book, and therefore, for the sake of convenience, valence bond theory has been discussed in terms of qualitative and non-mathematical terms only. To start with, let us consider the formation of hydrogen molecule, which is the simplest of all the molecules. Consider two hydrogen atoms A and B approaching each other having nuclei Na and Nb, and electrons represent in them are presented as Ea and Eb. When the two atoms are at large distance from each other, there is no interaction between them. As these two atoms approach each other, new attractive and repulsive forces begin to operate. Attractive forces arises between first nucleus of one atom and its own electron, that is Na Ea and Nb Eb. Second, nucleus of one atom and electron of other atom, that is NaEb and NbEa. Similarly, repulsive forces arises between electrons of the two atoms and nuclei of the two atoms. Attractive forces tend to bring the two atoms close to each other, whereas repulsive forces tend to push them apart. Experimentally, it has been found that the magnitude of new attractive force is more than the new repulsive forces. As a result, the two atoms approach each other and potential energy decreases. Ultimately, a stage is reached where the net force of attraction balances the force of repulsion and system acquires minimum energy. At this stage, two hydrogen atoms are said to be bonded together to form a stable molecule having the bond length of 74 picometer. Since the energy gets released when the bond is formed between two hydrogen atoms, the hydrogen molecule is more stable than that of the isolated hydrogen atoms. The energy so released is called as the bond enthalpy, which is corresponding to the minimum in the curve depicted. Conversely, 435.8 kilojoule of the energy is required to dissociate one molecule of H2 molecule. Orbital overlap concept. In the formation of hydrogen molecule, there is a minimum energy state when two hydrogen atoms are so near that their atomic orbitals undergo partial interpenetration. This partial merging of atomic orbitals is called the overlapping of atomic orbitals, which results in the pairing of electrons. The extent of overlap decides the strength of a covalent bond. In general, greater the overlap, the stronger is the bond formed between two atoms. Therefore, according to the orbital overlap concept, the formation of a covalent bond between two atoms results by pairing of electrons present in the valence shell having opposite spins. Directional properties of bonds. As we have already seen, the covalent bond is formed by overlapping of atomic orbitals. The molecule of hydrogen is formed due to the overlap of one s orbital of two hydrogen atoms. In case of polyatomic molecules like CH4, NH3 and H2O, the geometry of the molecules is also important in addition to the bond formation. For example, why is it so that CH4 molecule has tetrahedral shape and HCH bond angle is 109.5 degree, while the shape of NH3 molecule pyramidal. The valence bond theory explains the shape, the formation and the directional properties of bonds in polyatomic molecules like CH4, NH3, H2, etc. in terms of overlap and hybridization of atomic orbitals. Overlapping of atomic orbitals. When orbitals of two atoms come close to form bond, their overlap may be positive, negative or zero, depending upon the sign of the phase and the direction of orientation of amplitude of the orbital wave function in the space. Positive and negative sign on boundary surface diagram show the sign of orbital wave function and are not related to charge. Orbitals forming bond should have same sign, phase and orientation in space. This is called positive overlap. Various overlaps of s and p orbitals are depicted here also. The criterion of overlap as a main factor for the formation of covalent bonds applies uniformly to the homonuclear, the heteronuclear, diatomic molecules and polyatomic molecules. We know that the shapes of CH4, NH3 and H2O molecules are tetrahedral. pyramidal and bent respectively. It would be therefore interesting to use valence bond theory to find out if these geometrical shapes can be explained in terms of the orbital overlaps. Let us first consider the CH4 molecule. The electronic configuration of carbon in its ground state is helium 2s2 2p2, which is the within the excited state becomes helium 2s1 2px1 2py1 and 2pz1. The energy required for this excitation is compensated by the release of energy due to the overlap between the orbitals of carbon and the hydrogen. The four atomic orbitals of carbon, each with an unpaired electron, can overlap with the 1s orbitals of the four hydrogen atoms, which are also singly occupied, and this will result in the formation of four CH bonds. It will, however, be observed that while the three p orbitals of carbon are at 90 degree to one another, the HCH angle for these will also be 90 degree. That is, three CH bonds will be oriented at 90 degree to one another. The 2s orbital of carbon and the 1s orbital of hydrogen are spherically symmetrical and they can overlap in any direction. Therefore, the direction of the fourth CH bond cannot be ascertained. This description does not fit in with the tetrahedral HCl angle of 109.5 degree. Clearly, it follows that simple atomic orbital overlap does not account for the directional characteristic of the bond in CH4. Using similar procedure and arguments, it can be seen that in the case of NH3 and H2 molecules, the H and HOH angles should be 90 degree. This is in disagreement with the actual bond angles of 107 degree and 104.5 degree in the NH3 and H2 molecules respectively. Types of overlapping and nature of covalent bonds. The covalent bond may be classified into two types depending upon the type of overlapping, the sigma bond and the pi bond. Sigma bond. This type of covalent bond is formed by the end-to-end overlap of bonding orbitals along the internuclear axis. This is called as head-on overlap or axial overlap. This can be formed by any one of the following types of combinations of atomic orbitals: SS overlapping, SP overlapping, PP overlapping. Second is pi bond. In the formation of pi bond, the atomic orbitals overlap in such a way that their axes remain parallel to each other and perpendicular to the internuclear axis. The orbitals formed due to the sidewise overlapping consist of two Saucer type charged clouds above and below the plane of the participating atoms. Strength of sigma and pi bonds. Basically, the strength of a sigma bond depends upon the extent of overlapping. In case of sigma bond, the overlapping of orbitals takes place to a large extent, and it is stronger as compared to the pi bond, where the extent of overlap occurs to a smaller extent. Further, it is important to note that in the formation of multiple bonds between two atoms of a molecule, pi bond is formed in addition to a sigma bond. Hybridization. In order to explain the characteristic geometrical shapes of polyatomic molecules like CH4, NH3 and H2 etc., Pauling introduced the concept of hybridization. According to him, the atomic orbital combine to form new set of equivalent orbitals known as the hybrid orbitals. Unlike pure orbitals, the hybrid orbitals are used in bond formation. The phenomena is known as hybridization, which can be defined as the process of intermixing of orbitals of slightly different energies so as to redistribute their energies, resulting in the formation of new set of orbitals of equivalent energies and shapes. For example, when 2s and 2p orbitals of carbon hybridize, there is the formation of 4 new sp3 hybrid orbitals. Salient features of hybridization. The main feature of hybridization are as the number of hybrid orbitals is equal to the number of atomic orbitals that get hybridized. The hybridized orbitals are always equivalent in energy and shape. The hybrid orbitals are more effective in forming stable bonds than the pure atomic orbitals. These hybrid orbitals are directed in space in some preferred direction to have minimum repulsion between electron pairs and thus a stable arrangement. Therefore, the type of hybridization indicates the geometry of the molecules. Important conditions for hybridization. First, the orbitals present in the valence shell of the atom are hybridized. Second, the orbitals undergoing hybridization should have almost equal energy. Third, promotion of electron is not essential condition prior to hybridization. Fourth, it is not necessary that only half-filled orbitals participate in hybridization. In some cases, even filled orbitals of valence shell take part in hybridization. Types of hybridization. There are various types of hybridization involving sp and d orbitals. The different type of hybridizations are as sp hybridization. This type of hybridization involves a mixing of one s and one p, resulting in the formation of two equivalent sp orbitals. The suitable orbitals for sp hybridization are s and pz. If the hybrid orbitals are to lie along the z-axis, each sp hybrid orbitals has 50% s character and 50% p character. Such a molecule in which the central atom is sp hybridized and linked directly to other central atoms possesses linear geometry. This type of hybridization is also known as diagonal hybridization. The two sp hybrids point in the opposite direction along the z-axis with projecting positive lobes and very small negative lobes, which provides more effective overlapping, resulting in the formation of stronger bonds. Example of molecule having sp hybridization: BeCl2. sp2 hybridization. In this hybridization, there is involvement of one s and two p orbitals in order to form three equivalent sp2 hybridized orbitals. For example, BeCl3 molecule. In BeCl3 molecule, the ground state electronic configuration of central boron atom is 1s2 2s2 2p1. In the excited state, one of the 2s electrons is promoted to vacant 2p orbital. As a result, boron has 3 unpaired electrons. These 3 orbitals hybridize to form 3 sp2 hybrid orbitals. The 3 hybrid orbitals so formed are oriented in a trigonal planar arrangement and overlap with the 2 p orbitals of fluorine to form 3 BeCl bonds. Therefore, in BeCl3, the geometry is trigonal planar with fluorine boron chlorine bond angle of 120 degree. sp3 hybridization. This type of hybridization can be explained by taking the example of CH4 molecule, in which there is a mixing of one s orbital and 3 p orbital of the valence shell to form 4 sp3 hybrid orbital of equivalent energies and shape. There is 25% s character and 75% p character in each sp3 hybrid orbital. The 4 sp3 hybrid orbitals so formed are directed towards the four corners of the tetrahedron. The angle between sp3 hybrid orbitals is 109.5 degree. In case of H2O molecule, the 4 oxygen orbitals undergo sp3 hybridization, forming 4 sp3 hybrid orbitals, out of which 2 contain 1 electron each and the other 2 contain a pair of electrons. These 4 sp3 hybrid orbitals acquire a tetrahedral geometry with 2 corners occupied by hydrogen atoms while the other 2 by the lone pairs. The bond angle in this case reduced to 104.5 degree from 109.5 degree, and the molecule thus acquires a V-shape or an angular geometry. Molecular orbital theory. Molecular orbital theory (MOT) was developed by F. Hund and R. S. Mulliken in 1932. The salient features of this theory are: the electrons in a molecule are present in the various molecular orbitals as the electrons of atoms are present in the various atomic orbitals. The atomic orbitals of comparable energies and proper symmetry combine to form molecular orbitals. While an electron in an atomic orbital is influenced by one nucleus, in a molecular orbital it is influenced by 2 or more nuclei depending upon the number of atoms in the molecule. Thus, an atomic orbital is monocentric while a molecular orbital is polycentric. The number of molecular orbitals formed is equal to the number of combining atomic orbitals. When 2 atomic orbitals combine, 2 molecular orbitals are formed. One is known as the bonding molecular orbital, while the other is known as antibonding molecular orbital. The bonding molecular orbital has lower energy and hence greater stability than the corresponding antibonding molecular orbital. Just as the electron for just as the electron probability distribution around a nucleus in an atom is given by an atomic orbital, the electron probability distribution around a group of nuclei in a molecule is given by a molecular orbital. The molecular orbitals, like atomic orbitals, are filled in accordance with the above principle, obeying the Pauli's exclusion principle and the Hund's rule. Formation of molecular orbitals, linear combination of atomic orbitals, LCAO. According to the wave mechanics, the atomic orbitals can be expressed by wave functions size, which represent the amplitude of the electron waves. These are obtained from the solution of Schrödinger wave equation. However, since it cannot be solved for any system containing more than one electron, molecular orbitals, which are one electron wave functions for molecules, are difficult to obtain directly from the solution of Schrödinger wave equation. To overcome this problem, an approximate method known as the linear combination of atomic orbitals has been adopted. Let us apply this method to the homonuclear diatomic hydrogen molecule. Consider the hydrogen molecule consisting of two atoms A and B. Each hydrogen atom in the ground state has one electron in one s orbital. The atomic orbitals of these atoms may be represented by the wave functions psi A and psi B. Mathematically, the formation of molecular orbitals may be described by the linear combination of atomic orbitals that can take place by addition and by subtraction of wave functions of individual atomic orbitals as psi mo is equals to psi a plus minus psi b. Therefore, the two molecular orbitals psi and psi star are formed. Sigma and sigma star are formed. Sigma is equals to psi a plus psi b. Sigma star is psi a minus psi b. The molecular orbital sigma formed by the addition of atomic orbitals is called the bonding molecular orbital, while the molecular orbital sigma star formed by the subtraction of atomic molecular orbital is called the anti-bonding molecular orbital. Qualitatively, the formation of molecular orbitals can be understood in terms of constructive or destructive interference of the electron waves of the combining atoms. In the formation of bonding molecular orbital, the two electron waves of the bonding atoms reinforce each other due to the constructive interference, while in the formation of anti-bonding molecular orbital, the electron waves cancel each other due to the destructive interference. As a result, the electron density in a bonding molecular orbital is located between the nuclei of the bonded atoms, because of which the repulsion between the nuclei is very less, while in case of an anti-bonding molecular orbital, most of the electron density is located away from the space between the nuclei. In fact, there is a nodal plane on which the electron density is 0 between the nuclei, and hence the repulsion between the nuclei is high. Electrons are placed in a bonding molecular orbital tend to hold the nuclei together and stabilize the molecule. Therefore, a bonding molecular orbital always possesses lower energy than either of the atomic orbitals that have combined to form it. In contrast, the electrons placed in the anti-bonding molecular orbital destabilize the molecules. This is because the mutual repulsion of the electrons in this orbital is more than the attraction between the electrons and the nuclei, which causes a net increase in energy. It may be noted that the energy of anti-bonding orbital is raised above the energy of the parent atomic orbitals that have combined, and the energy of the bonding orbital has been lower than the parent orbitals. The total energy of the two molecular orbitals, however, remains the same as that of the two original atomic orbitals. Conditions for the combination of atomic orbitals. The linear combination of atomic orbitals to form molecular orbitals takes place only if the following conditions are satisfied. First, the combining atomic orbitals must have the same or nearly the same energy. Second, the combining atomic orbitals must have the same symmetry about the molecular axis. Third, the combining atomic orbitals must overlap to the maximum extent. Types of molecular orbitals. Molecular orbitals of diatomic molecules are designated as sigma, pi, delta, etc. In this nomenclature, the sigma molecular orbitals are symmetrically around the bond axis, while the pi molecular orbitals are not symmetrical. For example, the linear combination of 1s orbitals centered on two nuclei produces two molecular orbitals which are symmetrical around the bond axis. Such molecular orbitals are of the sigma type and are designated as sigma 1s and sigma star 1s. If internuclear axis is taken to be in the z direction, it can be seen that a linear combination of two p z orbitals of two atoms also produces two sigma molecular orbitals designated as sigma 2pz and sigma star 2pz. Molecular orbitals obtained from 2px and 2py orbitals are not symmetrical around the bond axis because of the presence of positive lobes above and negative lobes below the molecular plane. Such molecular orbitals are labeled as pi and pi star. A pi bonding molecular orbital has larger electron density above and below the internuclear axis. The pi star, the antibonding molecular orbital, has a node between the nuclei. Energy level diagram for a molecular orbital. We have seen that 1s atomic orbital on two atoms form two molecular orbitals designating as sigma 1s and sigma star 1s. In the same manner, the 2s and 2p atomic orbitals on two atoms give rise to the following 8 molecular orbitals: antibonding molecular orbital sigma star 2s, sigma star 2pz, sigma star 2px, and pi star 2px and pi star 2py. Bonding molecular orbitals sigma 2s, sigma 2pz, pi 2px, pi 2py. The energy level of these molecular orbitals have been determined experimentally from the spectroscopic data for homonuclear diatomic molecules of second law elements of periodic table. The increasing order of energies of various molecular orbitals for O2 and F2 is given as sigma 1s, then sigma star 1s, sigma 2s, sigma star 2s, sigma 2pz, pi 2px is equals to pi 2py, less than pi star 2px is equals to pi star 2py is less than sigma star 2pz. However, this sequence of energy levels of molecular orbitals is not correct for the remaining molecules Li2, B2, B2, C2, N2. For instance, it has been observed experimentally that for molecules such as B2, C2, N2, etc., the increasing order of the energy of various molecular orbitals is sigma 1s, then sigma star 1s, then sigma 2s, then sigma star 2s, then pi 2px is equals to pi 2py, which is less than sigma 2pz, which is less than pi star 2px, equals to pi star 2py, which is less than sigma star 2pz. The important characteristic feature of this order is that the energy of sigma 2pz molecular orbital is higher than that of the pi 2px and pi 2py molecular orbitals. Electronic configuration and molecular behavior. The distribution of electrons among various molecular orbitals is called the electronic configuration of the molecule. From the electronic configuration of the molecule, it is possible to get important information about the molecule as discussed below. Stability of molecule. If Nb is the number of electrons occupying bonding orbitals and Na is the number of occupying the antibonding orbitals, then the molecule is stable if Nb is greater than Na. The molecule is unstable if Nb is less than Na. In the first condition, more bonding orbitals are occupied and so the bonding influence is stronger and the stable molecule results. In second condition, the anti-bonding influence is stronger and therefore the molecule is unstable. Bond order. Bond order BO is defined as 1/2 the difference between the number of electrons present in the bonding and the anti-bonding orbitals. Bond order is equals to half of Nb minus Na. The rules discussed above regarding the stability of the molecule can be restated in the terms of bond order as follows. A positive bond order Nb greater than Na means a stable molecule, while a negative Nb less than Na or 0, that is Nb is equals to Na bond order means an unstable molecule. Nature of the bond. Integral bond order values of 1, 2 or 3 corresponds to a single, double or triple bonds respectively as studied in the classical concept. Bond length. The bond order between two atoms in a molecule may be taken as approximate measure of the bond length, and the bond length decreases as bond order increases. Magnetic nature. If all the molecular orbitals in a molecule are doubly occupied, the substance is diamagnetic. However, if one or more molecular orbitals are singly occupied, it is paramagnetic. For example, O2 molecule. Bonding in some homonuclear diatomic molecules. In this section, we shall discuss bonding in some homonuclear diatomic molecules. Hydrogen molecule H2. It is formed by the combination of two hydrogen atoms. Each hydrogen atom has one electron in one s orbital. Therefore, in all there are two electrons in the hydrogen molecule which are present in sigma 1s molecular orbital. So, electric configuration of hydrogen molecule is S2, that is sigma 1 S2. The bond order of S2 molecule can be calculated as bond order Nb minus Na upon 2 is equals to 2 minus 0 upon 2, that is 1. This means that the hydrogen atoms are bonded together by single covalent bond. The bond dissociation energy of hydrogen molecule has been found 438 kJ per mole and the bond length is equals to 74 picometer. Since there is no unpaired electron is present in hydrogen molecule, therefore it is diamagnetic. Helium molecule He2. The electronic configuration of helium atom is 1s2. Hydrogen bonding. Nitrogen, oxygen and fluorine are the highly electronegative elements. When they are attached to a hydrogen atom to form covalent bond, the electrons of the covalent bond are shifted towards the more electronegative atoms. This partially positively charged hydrogen atom forms a bond with the other more electronegative atom. This bond is known as hydrogen bond and is weaker than the covalent bond. For example, in HF molecule, the hydrogen bond exists between hydrogen atom of one molecule and fluorine atom of another molecule, as depicted here. Here, hydrogen bond acts as a bridge between two atoms which holds one atom by covalent bond and the other by hydrogen bond. Hydrogen bond is represented by a dotted line while a solid line represents the covalent bond. Thus, hydrogen bond can be defined as the attractive force which binds the hydrogen atom of one molecule with the electronegative atom, likewise fluorine, oxygen or nitrogen of another molecule. Cause of formation of hydrogen bond. When hydrogen is bonded to strongly electronegative element like X, the electron pair shared between the two atoms move far away from the hydrogen atom. As a result, the hydrogen atom becomes highly electropositive with respect to the other atom, that is X. Since there is displacement of electrons towards X, the hydrogen acquires frictional positive charge, delta positive, while X attains fractional negative charge, that is delta negative. This results in the formation of a polar molecule having electrostatic force of attraction, which can be represented as H delta positive, X delta negative, H delta positive, X delta negative. The magnitude of hydrogen bonding depends on the physical state of the compound. It is maximum in the solid state and minimum in the gaseous state. Thus, the hydrogen bonds has strong influence on the structure and the properties of the compounds. Type of hydrogen bonds. There are two types of hydrogen bonds, the intermolecular hydrogen bond and the intramolecular hydrogen bonds. Intermolecular hydrogen bond. It is formed between two different molecules of the same or different compounds. For example, hydrogen bond in case of HF molecule, alcohol or water molecules, etc. Intramolecular hydrogen bond. It is formed when hydrogen atom is in between the two highly electronegative like fluorine, oxygen or nitrogen atoms present within the same molecule. For example, in orthonitrophenol, the hydrogen is in between the two oxygen atoms. Thank you.